Hello, we are talking about thermochemistry, and today we're going to talk about endothermic and exothermic processes. So in this chapter, we've been talking about the heat that is transferred from one object to another. We know that the first law of thermodynamics says that the energy of the universe is conserved. So how come we're talking about energy being lost or gained or released or absorbed? Well, in chemistry, we think of the universe as a system and surroundings. So the system is whatever we're studying. It could be a chemical reaction, it could be a physical change, it could be a cup of water that I'm heating. So anything that we are actually studying is called our system. Everything else, so the rest of the room, the rest of the country, the rest of the universe, is all the surroundings. So the surroundings and the system together make up the universe. The energy of the whole universe is conserved. It can't be created or destroyed, but the system can release energy to the surroundings, or the surroundings can give energy into the system. So in terms of heat, we have two types of processes. We have exothermic and endothermic. So let's talk about what those mean. Endothermic, endo means in, thermic is heat. And whenever we're referring to something, we're usually referring to our system, not our surroundings. Whatever we're studying is our system. So when we say heat is going in, we're talking about our system. Heat is going into our system. Where is that heat coming from? It's coming from the surroundings. So this would be an endothermic process, where the energy is transferred from the surrounding into our system. In an endothermic process, we're going to feel cold. The reason is the energy that the system is absorbing, it's not going into heating it up, it's actually going into changing the position of the particles. So it's going into potential energy, position of particles, not temperature. But at the same time, because the system is absorbing energy in order to change its particles, its position of its particles, it's taking that energy from the surroundings, and the surroundings are losing the energy in terms of heat. And so the surroundings get cold. The surroundings and the system are mixed together or touching each other. And so everything gets cold. So we know that it's an endothermic process if it feels cold. Exothermic, on the other hand, exo means exit or out. Thermic, again, means heat. So the heat is going out of our system. Where is it going? It's going to the surroundings. So this would be an exothermic process where the heat is going out of the system, going to the surroundings. The energy that is lost by the system, that is again going into changing the position of the particles inside of the system. When it goes to the surroundings, it heats up the surrounding. It goes to the surroundings as heat. And so the surroundings get hot. The surroundings and the system are touching together, so everything gets hot. So that's how you know if it's an exothermic or an endothermic process. If it feels cold, then it's endothermic. If it feels hot or warm, then it's exothermic. So I have a candle that is lit here. So would this be an exothermic or an endothermic process? Well, my candle feels warm. As the wax is burning, it's giving off heat. And so that would be an exothermic process because it feels warm. So as the candle burns, it's dropping in potential energy. Its particles are rearranging and dropping in potential energy, and it's giving off that energy. The energy is going out of the system to the surroundings, and I'm part of the surroundings, so I feel warm. And the air around it feels warm. So that's an exothermic process. So any type of combustion reaction, or any type of explosion, or any type of reaction that gives off heat, that is going to be an exothermic process. So let's talk about exo and endothermic processes a little bit more, and we're going to draw an energy diagram for both of these. So I have an equation here that's a reaction. We're going to cross that out, and we're just going to write a generic equation. A plus B yields C plus D. A and B being the reactants, and C and D are the products. So we are talking about an exothermic process, which means the heat is going out of your system, going to the surroundings. And so again, the surroundings are going to get hot, and everything will get hot. Surrounding and system are touching each other. So exothermic processes feel hot or warm. So in our energy diagram, on the y-axis, we have the potential energy of our substances. And on the x-axis, we have either time or reaction progress. So at the very beginning, we have just the reactants, right? And the reactants, A and B, have a certain amount of potential energy. So let's say they have this much potential energy. These are my reactants. So what's going to happen in an exothermic process is the reactants are going to give off heat to the surroundings, give off energy to the surroundings. And so what's going to happen at the end of the reaction when we get to the products? Are the products going to have higher or lower energy than the reactants? Let's think about this. So reactants have a certain amount of energy, certain amount of potential energy. They're going to give off some of that energy, take it out of the system. So what are you going to be left with? You're going to be left with a lower potential energy. So your products are going to have lower potential energy. So in an exothermic process, some potential energy from the reactants was released into the surroundings. And so the potential energy of the products, what you end up with, is lower than what you started with, which is the reactants. The difference in the potential energy between the reactants and the products, that's how much heat or energy was released, was given off by your system. So this is delta H of your reaction, which is the heat or energy released by the system into the surroundings. So the reactants had this much energy, they gave away this much energy, so now the products only have this much energy left. So let's talk about this delta H, this heat of reaction, or the energy that's transferred in your reaction. So delta of anything is final minus initial. So in a chemical reaction, what you start with are reactants and what you end up with are the products. So when we say final minus initial, that would mean products minus reactants. So if we take the potential energy or the heat that the products have minus the heat of the reactants, so final minus initial, that's going to give us our delta H. So let's look at our values here. The products have this much potential energy. The reactants have this much potential energy. So if we take this number minus this number, so a lower number minus a bigger number, is that going to give you positive or negative? That's going to be a negative value. And so that's another way that you know that you have an exothermic process if the delta H is negative, because what that means is the products have lower potential energy than the reactants. So final minus initial is going to be a negative number. Let's think about delta T. Delta T is the change in temperature. So we said in an exothermic process, your system gives off energy to the surroundings. So the surroundings that are touching the system, everything gets hot, right? So if we measure the temperature, so if I start out, let's say, at room temperature, and then I have an exothermic process, and so it gives off heat, and so everything gets hot. So my final temperature is going to be hotter. It's going to be higher. And so if I do delta T, that's going to be T final minus T initial. Any delta is final minus initial. And so final temperature is hotter or higher than the initial, and so that's going to be a positive value. So that's how you know that you have an exothermic process, is if your temperature goes up, your delta T is positive. So delta H for exothermic processes are negative. Delta H is positive. They're opposite of each other. Now to complete this energy diagram, the energy doesn't just go poof down like that. What happens is you go up a hill first and then you go down. And the top of the hill here, this is called the transition state. Now the transition state is this complicated structure that looks in between reactants and products. It's a complicated structure where the reactant bonds are starting to break and the product bonds are starting to form. So because it's so complicated, it is very high in potential energy. As you can see, it's the highest substance out of everything in the reaction. And things that have high potential energy tend to be unstable. So transition states usually are unstable. And depends on what the transition state is, those can live for like a few minutes, sometimes even microseconds or picoseconds or femtoseconds, depending on what it is. But it's very, very unstable compared to like the reactants and the products because it has such high energy. The difference in energy between the reactants and where the transition state is called the activation energy. And the activation energy is basically a little push that you give the reactants in order to get them to start the reaction. So it could be like a little stir, it could be a little bit of heat, it could be a little spark or something like that to get the reaction to go. So for example, if I'm lighting a match, burning of a match is an exothermic process, right? It's giving off heat. But to get it to burn, you got to strike it. So you got to give it a little bit of a push to get it to go. So that's what the activation energy is. Since in an exothermic process, you are giving off heat, the system is releasing energy. We put the energy or the heat on the product side of the equation. So if you see an equation where there's energy or heat on the product side, that is another clue that it's an exothermic process because the heat is given off by your system. So just to review, you know that it's an exothermic reaction if it's getting hot, or if you see in your equation your energy is on the product side, or your delta H that you're given is negative, or your delta T is positive, or you're given final and initial temperatures and the final temperature is higher, or if you're given a diagram and you see that the products have lower potential energy than the reactants. Now let's look at the same thing for an endothermic process. So I'm gonna cross that out again and write A plus B yields C plus D as our generic equation. So in an endothermic process, the system is absorbing energy. System absorbs energy. Energy is going into my system. So because I'm taking energy, heat energy from the surroundings get cold, and the surroundings are touching my system, and so everything gets cold. So endothermic processes feel cold to the touch. The energy that the system is taking, that energy is not heating it up, it's actually going into changing the position of the particles, maybe separating them, maybe just making them a little bit higher in potential energy. So it's potential energy that's going into your system, not heat. So everything is getting cold in an endothermic process. So similar to what we did last time, we're going to say our reactants have a certain amount of potential energy. So in an endothermic process, those reactants absorb energy, they take in energy, and so your products are going to have higher or lower energy than the reactants. Well, if the reactants are here and they're absorbing energy, they're taking more energy in, then the products would have higher energy than the reactants. So maybe my products are right here. So some potential energy was absorbed from the surroundings. So the products have higher potential energy than the reactants in an endothermic process. So the difference between the potential energy of the reactants and the products is your delta H of the reaction. So that's the heat that's transferred. In this case, this is the heat absorbed by the system. So let's look at the sign of the delta H. So we're going to do products minus reactants, final minus initial. So the products are right here, the reactants are right here. We're going to do products minus reactants. So high number minus smaller number, that's going to be a positive value. So if you're given a delta H and the value is positive, that tells you that it's an endothermic process. Your delta T, the change in temperature. So let's say we started out at room temperature and then we did an endothermic process. Well, it's going to absorb energy from the surroundings, so the surroundings are going to get cold, and so the final temperature is going to be a colder temperature. So when we do T final minus T initial, my final temperature is colder or lower than my initial. So low number minus high number, that is going to be a negative value. And so you know that it's an endothermic process if delta T is negative. To continue our curve like we did last time, it doesn't go just straight up. It goes through a hill like this. The top of the hill, that's your transition state. So again, that's something that is an unstable, complicated structure that looks in between like the reactants and the products. And it's highly unstable because it has such high energy. The difference between the reactants and the transition state, that's your activation energy. So that's how much energy you need to give the reactants in order to get the reaction to go. And then finally, in an endothermic process, because your system is absorbing energy in order to form the products, we put the energy or the heat on the reactant side. So to review, you know it's endothermic if it's getting cold, if you see the energy on the reactant side of an equation, if your products have higher potential energy than the reactants, if your delta H is positive, or if your delta T is negative, your final temperature is lower than your initial temperature. That tells you that it's an endothermic process.